Okay, welcome everyone to this continuation of Magma. Magma in a nutshell. Third lecture or second lecture, the third lecture, fourth lecture or third lecture, depends how you count because I had a zeros lecture. And essentially I would talk a little bit about lattice theory and the algebras and Lie groups and all that fun stuff and how to set them up in Magma, at least just to give you a little hint about it. As usual, there's a lecture associated by Don, which has more details, but I've kind of tried to run everything live in the online calculator, which is kind of the point. So recall, we have lecture notes that we see now in front of you, and we have the online calculator. Okay, fine. And well, I would like to construct a certain, well, Magma has everything built in already, but I would like to show you the construction because it's kind of nice. And the construction of a certain type of root system. I start with, you can guess on your way what root system it is. We start with the algebra of octonions, which really has just 8 elements. Well, E1 is the unit, and then E2 up to E8 with the usual roots that you think it is, and we'll try to explain it in a second. So essentially, the non-trivial elements are the points of the Fano plane, and the multiplication is given by this times this is this, right? So that's the multiplication. So EI times EJ is EK. Essentially, EI times EJ is EK up to a sum. Okay. Remember that we can set up the points on the Fano plane like this, or the Fano plane as follows. We'll do that in a second. And there's a silly shift involved, simply because Magma starts counting differently than I would like it to count. And that's all. Essentially, this is just mimicking the rule I just told you. Point times point is point up to the sum. And we'll see that in a second. And don't worry about the shift. It's just Magma's internal counting starts not where I wanted to start. That's essentially what happens. And we are going to use this code to set up an algebra. So it's just algebra, takes a ring, takes a dimension, and takes a multiplication table. So this is a bit annoying. So you need to give it a multiplication table, and you somehow need to specify everything. There are different ways of doing it. There are algebras given by generators and relations, for example, that we could set up. But this is called a structure constant algebra, right? It determines by the multiplication table, so by the structure constant. So everything you don't give it, so you need to give it those guys. Yeah, everything you don't give it is automatically supposed to be 0. And T contains 4 tuples of I and J and K, so I and J and K and the coefficient. Fine. So for example, if I would write down something like this, I1 minus 1, then this is saying EI times EI is minus 1, right? This is a scalar in front of the identity. So EI times EI is minus 1, which is one of our relations here. This, for example, would say 1 times I is I. So 1 is a unit. And similarly, I times 1 is I. So these are just setting up the unit relations, the second one, and the I minus 1, so the first relation here. And the Fano relations are set up like this. You just keep track of the sign. So essentially, Fano, the thing in the Fano plane, and the second point, the third point, and then there's a sign. Okay, so let's try to do that. Let's grab everything and put it in the online calculator. So here's our Fano plane. So this ordered set point is what it is. And now we set up our T here. Fair enough. So take T, set it up. T, so this is the rule in the Fano plane. So we can have a look at T if you want. T, group, this was what T, T. The rule in the Fano plane is this is a multiplication table. It just looks ugly. I will give you a nicer version of the multiplication table in a second. And then we just concatenate the additional rules that we have, and that's then our new T. So let's do it here, and it will be bigger than the old T. So they had some extra rules. 8 times 1 is 8. This is scalar 1, for example. Okay, fine. Nothing super exciting happening, just setting up the multiplication table. And then the octonions are defined as, well, I do it slightly differently than with the command here. So it's the algebra in an 8-dimensional space with our multiplication table over a ring, and then if you set it up as a function in the ring, I can give it a ring later. we'll do that in a second. So it's a function in the ring. So for example, you could do something like just over the integers, and let's see what happens with this piece. So OZ is now a friend, octonions over the integers. Algebra of dimension into a space ring integer ring. Very good. That makes some sense, I hope. And now let's print the multiplication table, and let's just do it first, and then I explain what's going on. So let's do it, put it here, and submit. Okay, so I just set up a polynomial ring in 8 variables to keep track on what is what, and then just really print the multiplication table. So E1, E2, E3, whatever, and you already see here in the first row and column that E1 is identity, and then whatever it is, multiplication table. And I should zoom in a little bit for you. Much better, much easier to see. There you go. Right, so I just printed the multiplication table. So O is now really just set up. It's just related to octonions set up even via a multiplication table. That's just what I did, and I just printed it using variables, so that gets a little bit easier to see. Right? Okay, so let's talk a little bit about an element in the octonions. So for example, you could do something like Z defined as OZ.1. Oh, I should do it this way. Okay, and we can get rid of the multiplication table. So just OZ.1, and let's print Z. Okay, and actually, OZ.1, it treats those elements as a tuple. So first entry is the coefficient of the E1, second entry is the coefficient of E2, and so on. So right now it's just, hopefully clear. This one will be this vector and so on. But it treats the elements as kind of vectors that have some multiplication rule. For example, I could do this, and it would tell me, okay, that's -1 times whatever, right? And I could do whatever. I could do this. There's a ring structure there. I hope that makes some sense how this works. Okay, it's hopefully clear what it does. Okay. Then there are some natural operations you can do on octonions. You can take the conjugate, you can take the trace, or you can take the norm. And I, of course, did it the wrong way around. You can conjugate it, and conjugate is just add a sign in front of everything that's not the identity. Taking the norm is just its conjugate, and taking the trace is this expression, which if you just think what the conjugate is, it's just really twice the first element. So let's just set that up as a function in our octonions. Okay, function that takes xi and returns its conjugate. That's essentially what happens here. The norm takes xi and returns the norm of that element, right? So because it's xi times its conjugate. So we can try that now. We can do something like Z again defined as OZ3 plus OZ4, something like that. And we can try to do conjugate of Z. Let's see what happens. Okay, maybe I should display Z itself, right? It just puts a negative sign in front for everything that is not the identity. I could put a 1 here, right? 1 and 1 stays the same. Or I could go to a norm of that element, whatever. Or I could go to trace of that element, whatever. Really just setting up those functions, computing traces and norms in the octonions. That's all that it does. Not that exciting, but of course, also good to know. Fair enough. Cool. So here's then just some example. If you want to set it up over a function field, for example, we could do it over a function field and just compute the various type of things. There you go. And the element x itself, let's just display x. X is just v1, v2, whatever. The element x itself is just this element. That's v1 times e1, v2 times e2, and so on. And you get a compute norm, trace, and whatnot. So let's get rid of this, or let's just keep it for now. We'll see what. So I hope that makes some sense. It's really just a calculation in an algebra. And you can set up any algebra you want and any type of calculation you want to do with that algebra. Okay, so why did I do that? Well, let's do the following. So a lattice is just a free Z module with some defined bases. Fine. So here, for example, you can set up a lattice by just taking a matrix, and the basis will be given by the row vectors of that matrix, unless they are linear dependent, then let's ignore the case when they're linear dependent. But essentially, you can just set it up. So let's just do it, and then we go back to Octonian. So I take another window and just set it up. Full vector space of degree 3 over the rational field. So that's the vector space of the rational field. It's a lattice of L. It's the ambient. I just printed the ambient space. I could also print L itself, and then it's the lattice of rank 2. It has 2 and degree 3 with whatever determinant and basis given by whatever. It already performed a Gaussian elimination to get a slightly nicer basis. The Gaussian elimination is always an operation you can perform on lattices. You can ask for the rank, whatever. Okay, so let's go back to our friend, the Fano plane. We want to make it into a certain type of lattice. We make it a little bit bigger. Okay, and we want a lattice in the Fano plane is really some kind of elements that are integral. So things that have norm and trace that are integers. An example would be if you just define everything over the integers, but they are more subtle integral elements in the Octonians, and we are looking for the maximum. Okay, so let me go back to the definitions here. So the lattice is this one. A finite dimension algebra is an order if it's a lattice, so there's some bases. And we are looking for some maximal orders in this guy that contain the obvious one. There could be something more subtle, right? Because I'm saying an element is integral if its norm and trace are integers, not necessarily that the constant itself in front of the bases are integers. And it turns out that there is actually a sub-lattice of order 240 inside, and that's kind of the maximal one, and it forms a certain type of algebraic structure that is called a Mu-Fang loop. And the way to set this up in Magma is as follows. I just did that here, so we don't need that crap here anymore. So X include, there's a certain way of doing it. It's nicely written in various forms of the literature. But anyway, so I need to define a certain set X. And essentially, the set X is including H. H is a line in the Fano plane, and the pi is just conjugating by a certain type of permutation, permuting the first two variables. And you get kind of those guys here. So this is, for example, a line in the Fano plane, and in this case, the first element is just what it is. So nothing really exciting happening. Just setting up a certain set X. Okay, that's essentially it. And you can beam it up into a certain object, which is called a Mu-Fang loop. I leave it to you to figure out how that works. I just copy it and put it here. Very good. And it's whatever. It's a 240 element set, which is multiplicatively closed. That's all. That's what I'm checking. For all x and y, is it true that x, y is in M? Yes, it's true. The order of M is 240. I just wanted to set up this one. Okay, so you can set it up from the kind of the orders within the Octonians. And okay, fine, fair enough. But the point is, we can use that as follows. We can just set up in this thing a certain type of operation, which I will do in a second for you. So you just set it up, certain type of operation. It gets longer and longer. So it's a function that just does the following. It takes an A and a V, and it uses the conjugate from before, divides by the norm. That's essentially setting up a reflection in this Mu-Fang loop. It's really just a reflection, just written in terms of the loop. And I just want to pick up the reflection matrix, which is just now in the matrix ring. Okay, and the other thing that just sets up whatever it is, so no output yet. So I set up reflections in the Mu-Fang loop. Is a function A and V that does this operation, which is exactly how reflections look like in the Mu-Fang loop. It's kind of a calculation that you can do. Okay, so that's what's happening. And it turns out that the Mu-Fang loop is a root system with, well, simple roots and all that fun stuff. So let's just set it up for you. So I just put it here. So the Mu-Fang loop gives you a root system. Let's just put everything here. of order 120, in this case, a piece of order 120, and these are the positive roots of the root system, and there are simple roots of the root system. In any case, you can just set it up as a root system. I don't need this one anymore, and you will get can ask it for the Catan matrix associated to the root system. And the Catan matrix associated to the root system is this beast, and let's just look it up what it is. Graph online RU. So because our little friend Magma is not really fantastic in displaying these things, the problem will be that this is a adjacency matrix. So this is a Catan matrix. To get the adjacency matrix, you put the 2's to 0 and the 1's to -1's. You probably don't need to do that. So let's see what happens if I put the 2's to 0 and then press console because I'm an idiot. Let's try it again. Let's put the 2's to 0 and then hopefully press save instead of console. God, that was stupid. Thank you so much, brain. Press console, press save. And it doesn't do anything. Why? Because I also need to get rid of the -1's here. We can keep the 2's. So just get rid of the -1's here. Very good. I should have prepared this in advance. But anyway, you get the point. I can get onto the 2's, 0, 0, 0. Now, looks a bit weird. So maybe we can arrange that graph somewhat. That looks a little bit nicer. It actually should be the type E8 Duncan diagram. And it is kind of is. It is type E8 Duncan diagram. Okay, from all that nonsense, and it's really much better to just look in the file and see how it goes. We can construct the type E8 root system from the octonions. That's essentially what it is. Yeah, and this is the Catan matrix of this root system. And I can ask that in Magma. So I just wanted to display this guy. I could just say, okay, what is the Weyl group or the Coxeter group associated to it? And what is actually the root system of that shitty Catan matrix? Well, and it will tell me it is actually, I can get rid of the Catan matrix. It is actually the type E8 Duncan diagram in this labeling, with 1 being the bivalent vertex. So you can set up the kind of the type E8 Duncan diagram just from just the octonions. Okay, but of course you can also do it directly. So Magma has things built in that might not come as a surprise. Hopefully it doesn't come as a surprise. So we have built-in functions. We don't need to do the whole Fano. We can just say E7, for example, and we can just say Duncan diagram of the RD, in case I can spell Duncan diagram. And this would be E7. We could have gone for E8 or whatever. You get the point. So everything is already built in. You just need to use this one here. And there's some silly difference whether you want the adjoint system or not. Let me not worry about that too much. Right? So there are different ways to include the root system, whatever. And yeah, we want the simply connected one of dimension 8. So we can do the same for example, the whatever type G2. What are the simple roots in type G2? The simple roots in type G2 are very boring in terms of the standard basis. What are the simple co-roots in type G2, for example? They're a bit more interesting in terms of the standard basis. What is a Catan matrix in type G2? Well, let's have a look what the Catan matrix is in type G2. And it is, well, let me just get rid of those guys here. It is just this Catan matrix. What is the Duncan diagram of this type? The Duncan diagram of my friend RB. Let's have a look. I definitely want to put a semicolon here. Yeah, that looks like G2. So everything is already built in, simple roots, whatever, fundamentals, roots, whatever. All of that stuff is built in into Magma, the Catan matrix. And you can even define something like the reductive group of that type. Well, let's just do it. Again, root datum G2. And let's say I take a Galois field of order G of 5. and let's do the group of Lie type G2 with coefficient and GF5. That's some finite group of order. It's a quite impressive order, actually. I wasn't aware that it's this big. Obviously, that's not so difficult to check, but I wasn't aware that it's this big. Okay, Magma has no problem to setting those up. If you want an algebraically closed field, that gets more tricky, but there's a package for Lie algebras that you would need to load, but I can't run it here in the online calculator. But with finite fields, there's no problem at all, and you can just set up the finite fields, and you can just play with the highest rate representations, for example, of that object. So we still have our G here, and I just defined it now over GF3. Why not? So let's do the same. Group of Lie type, still same root system GF3. You can ask for the highest rate representation of that beast, and it will tell you it's a 77-dimensional representation over that field, given by a certain type of rule that it's not outputting in this imperfection. But you can set up highest rate representations, and you can have tensor product, take tensor products of them, ask whether they're irreducible or not. Right, let's just do it for all of that fun stuff. So it has Lie theory essentially built in. Unless you're really worried about Lie theory or algebraic closed fields, that's more difficult. You would need to load a package. But for finite fields, you can just do it directly from the root system, and it will do, well, essentially everything you want for you. For example, let's try this one here. So let's set up again the root system in type G2. There you go. And in a certain type of fashion, however, Dupin diagram of RB will be, well, there you go. It's still all type G2. And now let's do it over a function field instead of over a finite field. That's also no problem. As long as it can do explicit calculations, Magma will be very happy. So function field, we set up the root of G2 over the function field, and we just take, for example, a product of certain elements of that group. No problem at all. As long as the field is numerically precise, so there's no complex numbers or real numbers going on, you can just set it up, and it has built-in highest rate representations, right? So for example, it has a built-in standard representation, it has the torus in terms of the standard representation, and all that fun stuff. So here, standard representation, so whatever, usually, unless you're in, well, almost always this is a minimal dimensional, non-trivial representation. But anyway, well, you can set up what is the torus in that standard representation. It will be a certain type of diagonal matrix. The standard representation that's just outputted. STB is just a 7-dimensional representation. It's in this case a 7-dimensional representation of the G2 Lie algebra over that field. And you can just do all that stuff, right? And you can just get it from the octonions as well. Anyway, let me do one more for you. We could have just set up E8 itself as just what is the standard representation of E8 over GF5. Let's hope E8 was not a bit too sophisticated for the online calculator, because E8 is rather large. Okay, it's a 200 and whatever dimensional representation with GF5, and then you can play various games with those representations. Anyway, so that's what I wanted to tell you about root systems. So we had, so Magma has all the Lie algebra stuff already built in, and I just explained to you this funny construction. I kind of didn't really explain it. It's in the file if you really want to read it. The construction of the type E8 root system from the octonions using the algebra construction in Magma. Anyway, I hope you enjoyed this video, and I also hope to see you next time.